So let us see now how all these things that we have learned about analytic functions help us in solving problems in elasticity. Let's start from the easier end. Let's start with antiplane shear. If you remember, the antiplane shear condition is that displacements u1 and u2 are 0 all over the plane, and u3, the out of plane displacement, is the only displacement component, but it depends on x1 and x2 only. So on a body, you don't have any e1, e2 displacements, but you have either displacements coming out of the plane, which is u3, and u3 depends on x1 and x2 only. It does not depend on x3. So under these conditions, you can easily show that epsilon 3.1 and epsilon 3.2 are the only non-zero components of strain, and therefore in isotropic elasticity, sigma 3.1 and sigma 3.2 are the only non-zero components of stress, and the constitutive equation, Hooke's law, suggests that sigma 3.1 is mu times epsilon 3.1 and sigma 3.2 is mu times epsilon 3.2. That's how the shear stresses and strains are related in the generalized Hooke's law. So if you now put this into the equilibrium equation, you will see that the first two equilibrium equations for I equal to 1 and I equal to 2 are identically satisfied, trivially satisfied, 0 equal to 0. It's only the third equilibrium condition, that is sigma 3j comma j equal to 0. This is the third equilibrium equation, and this will lead to sigma 3.1 comma 1 plus sigma 3.2 comma 2 equal to 0. In place of sigma 3.1 and 3.2, put this, and you will end up with a harmonic equation in U3. So U3 del square U3 equal to 0 is the governing equation that rolls in this assumption: the strain displacement relationship, the constitutive equation, everything is rolled into this equation. And now you have to find a U3. You have to find a U3 that satisfies the harmonic equation, and of course whatever boundary conditions are applied. We'll see to that. So we already know that the real and imaginary parts of analytic function satisfy the harmonic equation. We already know that. Therefore, what we can do is we can write mu times u3 as the imaginary part of of an analytic function omega z. So omega z is an analytic function. So omega z is probably u plus iv. Omega z bar is u minus iv. So we subtract the two, divide by 2i, and that gives us the imaginary part v, and that imaginary part we assume is equal to mu u3. So this is our assumption. So we have transformed the problem of finding u3 to the problem of finding an analytic function omega z. Now once you have u3, the stresses are calculated in a straightforward way. So we use the fact that omega derivatives of omega with respect to z bar are equal to 0 because omega has been assumed to be analytic, and derivatives of omega bar with respect to z are equal to 0 for the same reason. We have already seen that this is the case. The conjugate is not a function of z, and the function itself is not a function of z bar. So we have already seen that. Using this, we can find the stresses. So remember, del x was expressed in terms of z quite some time back. I'll go back there. So del x was del z, del z bar. So using that, so let me go back to, yeah. So then del x is equal to half del z plus del z bar, and so let's call this del x1, and then if you take the first derivative of this, then you get mu times del u3 del x1 is equal to sigma 3(1), and that becomes equal to half del z plus del z bar, or is it just del z? This half is not there, sorry, this half is not there. So you get this times 1 by 2i omega minus omega bar. This is what you have. Then you have del z of omega, del z of omega bar, which is 0, then del z bar of omega, which is 0, and del z bar of omega bar, and you get this relation. Similarly, using del y, which is del x2, the definition of del x2, you get this equation. So sigma 3(1) in terms of omega is this, sigma 3(2) in terms of omega is this. We have done nothing great. We have just translated the problem from one of finding u3 to one of finding an analytic function. Okay, so combining the two stress equations. So we combine the two stress equations, sigma 3(2) plus I sigma 3(1) will make the omega bar cancel out, and this is what you can easily show from the above two equations. So these are the stresses. So once we find omega, we will be able to find omega prime. Then the real part of omega prime will give you sigma 3(2). The imaginary part of omega prime will give you sigma 3(1). So it is just a compact way of writing the stresses. Now let us look at the boundary conditions. Remember, when we traverse the boundary, we traverse it always in a manner so that the domain is on our left. So we do it in a counterclockwise fashion. So this is the tangent at a point which has coordinates x1, x2. So this tangent is dx1 ds, dx2 ds, where s is a parameter that increases along as you move along the boundary. So suppose you have loads applied in this red part, which lies between S1 and S2. S starts at 0 from somewhere and then increases along the boundary, and here it is equal to S1. And then over this red part, you have loads applied, you have fractions applied up to the point S2. So these are 2 points on the boundary between which you have loads applied. And then we will have to apply this equation, Ti equal to sigma ij nj, which is the Cauchy relation. So n here has 2 components, n1 and n2, and sigma ij has only 2 components that are non-zero, which are sigma 3(1) and sigma 3(2). Right? So the only traction component that can come into picture is, so I can have sigma 3(1) n1 plus sigma 3(2) n2 equal to T3. That's the only traction equation that comes into play. All others, for example, T1 will be identically equal to 0, T2 will be identically equal to 0, T3 either coming out of the plane or going into the plane is the only traction component in an anti-plane shear problem. Okay, so this is what we are going to calculate, but before that we need this n. We need this n, and the T and the n must form a right-handed triad. So it must form a right-handed triad, and your S is increasing in this direction. In this direction it is increasing, and then you can do some small geometry. Say T is del x1 del s, this is the tangent, E1 plus del x2 del s E2, and this will, to form a right-handed triad, your the other vector in the triad must be into the plane. If T and N, T and the outward normal form a right-handed triad, then the other vector must be E3 minus E3. It's not plus E3. Plus E3 is coming out towards you, minus E3 is going in, and minus E3 will form the right-handed triad here. If you are here, then plus E3 would form the right-handed triad. Okay, here minus E3 would form the right-handed triad with T and N. And if that is the case, then N would be given by minus E3 cross T. So that is what happens in a right-handed triad. And if you do this minus E3 cross T, you will see that the components of N are this dx2 ds and minus dx1 ds. These are the two components of N. And now we have the components of N, N1 and N2 we have, and we have an expression for sigma 31 and sigma 32 in terms of omega. So we are going to put that in and write the traction on this part. Once we have the traction on this part, we can calculate the total force applied on this part, which will be some F3. It will be force in the 3 direction, which would be contour integral from S1 to S2 or over this path of T3 ds. So this would be the total force applied on this part of the boundary provided the out of plane thickness is taken as 1. Remember, T3 times area is what gives you the force, but we have taken the width, out of plane width, to be 1, so it's just the length. So the length is ds S1 to S2 is the total length of that portion over which tractions are applied. So so that's what we are going to do. We are first going to calculate T3 in terms of omega, and then we will calculate F3 in terms of omega as well. So these are our N's. N1 is this, N2 is this, we have already seen, and T3 is sigma 31 N1, sigma 32 N2. And now we are just going to put in N1 and N2. Sigma 31 is this, sigma 31 is this, sigma 32 is this. Plug in N1 and N2. N1 is here, N2 is here, plug everything in, and then calculate the force as T3 ds from S1 to S2, and you should get this expression. It's pretty simple to do. As you can see, this part is d ds of x1 plus ix2, this part, and this part is d ds of x1 minus ix2. So this is dz bar ds, and this is dz ds. Luckily, we get very simple expressions. So we have del omega del z dz ds plus del omega bar del z bar dz bar ds. But remember, omega is only a function of z. So del omega del z is same as d omega dz. So this is actually d omega ds. Integrated over ds would give you omega from S1 to S2. And this omega bar is a function of z bar only. So this is as good as d omega bar dz bar. So this would give you omega bar from S1 to S2. So omega minus omega plus omega bar would give you the real part of omega. So this expression finally becomes the real part of omega at S2 and the real part of omega at S1, and there's a minus sign here. So minus of the real part at S2 plus the real part at S1. You should you should derive this expression on your own. I've just given you all the steps, and this is what the force is. I call it Fs, but it is either out of the plane or into the plane. It is in the three direction, and that is something you should remember. The force, the traction in case of anti-plane shear problem is always either out of plane or into the plane, right? So now we have all the equations. So this is how we solve for the displacement. We have assumed this this is given by the imaginary part of omega. Sigma 32 and 31 are given by omega prime, and the force is the real part of omega z from S1 to S2, minus of the real part of omega z from S1 to S2. So these three are the equations that define the anti-plane shear problem in terms of complex variables. So what have we achieved here? What we have achieved is we have to determine just this. Once we determine this, then the displacement, stresses, everything get known automatically. How do we determine it? We determine it through a boundary condition like this. So if you know the force that you have applied on part of the body, that will give you an idea of what this omega z is going to be, because the force is related to the real part of omega z from S1 to S2. So that will give you an idea of what the omega could be, and then you can use that omega to get the displacements and the stresses everywhere inside the domain. Okay. Now this is for an anti-plane shear problem, and next we will look at it for a plane problem, a plane strain problem, which can also be translated very easily to a plane stress problem, but we will solve it for a plane strain problem in the next lecture.